So, Lee Smolin, welcome to Oxford. I very much enjoyed your new book, Time Reborn, which you're just about to talk about. And in the book you argue very much that you believe that time is real. And I think for most people, they wouldn't disagree with you, that there's a feeling like when they're watching this little interview back, that obviously happened in the past, the things are going to happen in the future. So perhaps in our journey, and it's the journey you take on the book, you have to take the reader first of all to the belief of physicists that time isn't actually real.
Well, it's not just physicists, Marcus. Many people live a kind of double life with respect to time, because we all live in the moment, we all perceive what we perceive, experience what we perceive in the moment, we perceive that to be one of the flow of moments. But many people, for different reasons, believe that behind this reality caught in time, this time-drenched reality that we live in, there's some timeless truth, some timeless reality, which is a deeper version of reality. And whether it's for philosophical reasons, or religious reasons, or reasons of belief in mathematics, or belief in timeless laws of nature, we all seem to have that problem. And so that's the contradiction that I propose to resolve.
I mean, you do take a bit of a pop at my field of mathematics.
Not at all.
Well, in the sense, I suppose, that that's the belief that mathematics and physical reality are the same. That you seem to distance a little bit the idea of eternal truths in mathematics is something slightly different to what we're doing, trying to describe the world around us. Is that right?
Well, I've no critique of the usual practice of mathematics or physics for that matter. What I have a critique of is the mysticism that many mathematicians seem to have, that when they're doing mathematics, they're exploring some other realm, either equally real or more real, or the only thing that's really real, of mathematical truth. Mathematical objects, once invented, have properties which are time independent if they're investigated at any time. Once the questions are formulated, once the axioms are laid down, the consequences can be followed through at any time, and they're timeless in that limited extent. But I don't think they exist before or without their being invented.
All right. I mean, that's very interesting, because I think all mathematicians have that kind of split feeling of, am I discovering or am I creating something? But you would say, in some sense, it is an act of creation which then has a timeless quality to it.
Yes, and I believe that nature is able to invent things which are also novel, which imply patterns, which then have true things about them.
Right.
And I think that our imagination, as mathematicians as well as in other domains, is capturing and focusing something which is inherently a facility of nature.
One of the things I found so striking about your book is your kind of thesis that physics in the past has been trying to find, in some sense, the laws which govern the universe, the mathematical equations, but you have a much more biological approach, in some sense, to what you think the laws of physics will look like, a more evolutionary idea. Can you explain that?
Well, if something is outside of time, but it acts within time, it's inexplicable. It's not enough anymore to say what are the laws of nature. It's enough to, if you want to describe the experiments going on at CERN, or what an astrophysicist observes in a star or in a galaxy, that's fine. You can deduce from observation that certain laws seem to be applying, and these laws are very general. But it's incorrect to extrapolate from that to say the laws are truly timeless, truly there for all time. Because if they are, there's no way to explain them. And this was understood a long time ago. It was understood in the late 19th century by the philosopher Charles Sanders Peirce. And it's not news to philosophers, although I had the painful experience of discovering this line of thought on my own.
And was it really a moment of change for you as a physicist in the way that you approached your physics?
Totally. I went into physics to discover these timeless truths. And for me it was about 1988. And the crisis was the plethora, the enormous variety of string theories, which had been discovered, in particular by Andy Strominger, who's a friend of mine. And Andy said to me he had upped the number of string theories from hundreds of thousands to an uncountable version. And he said to me, there's so many that it won't be any use to try to figure out which one describes nature, if one describes nature. Because even if string theory is not true, it's very unlikely that there's one version of it that would match the experiments so far.
Yeah.
And I went away from that conversation and thought, well, how would nature have chosen which laws out of all this infinite number, or vast number of possible laws? How would nature have made a choice? And I began to read at that time. I was also very impressed by the anthropic argument, not by the correctness of it, because I think as an argument it's incorrect, but the observation that the parameters of the laws of nature are chosen very delicately in ways that lets chemical complexity exist, that lets the world be astrophysically complex, and the two of them interact to form many massive stars and hence black holes and so forth. The whole complexity of the universe on a vast range of scales is contingent on fine-tuning of the values of the fundamental parameters. And I was very impressed by that, and I started to try to ask myself, where in science is there a method for explaining why some choices have been made in a way that leads to greater complexity than other choices through some natural process? And the only example I knew of was biology. And so I began to read the biologists like Richard Dawkins and Steve Gould and Lynn Margulis and people like that, and went looking to emulate or find a formal correspondence between the cosmological model and the way, because I learned from him what was essential in making natural selection work as an explanation. And I invented an idea around then, which is called cosmological natural selection. And part of my point is that why you go to time-changing laws, why you go to evolving laws, is that then the process of what chose the laws is something which is in our past, which means it may have consequences that can be observed in cosmological observations or in certain features of the present.
Which makes it quite distinct from the idea of the multiverse as a string theory, which is, you mean that now these many different sort of universes that might evolve with different equations will leave some sort of heritage that we can actually test.
Well, this is neutral with respect to string theory. This is completely neutral. And I was inspired by an issue in string theory.
Right.
And if string theory turns out to be correct, this is applicable to it. What you mean when you say the multiverses of string theory is that something peculiar happened in Stanford in the early 2000s, where the issue of the landscape of string theory, which is my name for the problem, for the space of the possible string theories, was hijacked by some of the cosmologists at Stanford who had their own multiverse theory connected to inflation.
Right, okay.
And so then this connection was made. But it's not all essential. Eternal inflation, as it's so called, is a way of generating a vast population of universes. So is cosmological natural selection. The difference is in cosmological natural selection, there's a lot of structure because the universe has a parent, which has a parent, which has a grandparent, and so on through many generations. And the structure of heredity counts in tuning the properties.
Right.
The same way as in biology, whereas in eternal inflation is just this primordial soup of eternally inflating, quote, vacuum. And the universes pop out of it like bubbles with no relation to each other and no structure, just random properties.
So your idea is that, for example, in a black hole, a new universe might form with slightly changing equations, and it's a kind of survival of the fittest theories that will actually grow something or not. Is that?
Yes. Yes. I took over an old idea, which was in the field, which is that the singularities at the end point of black hole evolution, where time is supposed to end inside a black hole, are removed by quantum effects, which is an idea now in models of quantum gravity that we have good evidence for. And once that's removed, time continues into the future in what used to be the future of the black hole, in the new region of space and time. And so if that region persists to exist, that defines what was called the baby universe,
Right.
the region of space and time. And there was also the postulate by John Ritter that the laws of physics change randomly when that happens. So all I had to contribute was that change, the hypothesis that change be small, so that fitness could accumulate, fitness being a universe's most fit, or a set of parameters are most fit, if those laws governed by those parameters will lead to the more black holes being produced than other sets of parameters.
I think what's very interesting, and it seems to be really something of our time, is this connections between other subjects, physics talking to biology, and you end the book actually with a chapter which is dealing with the implications of if time is real to sort of social economics, to economics, to climate change, even to consciousness as well. And this is quite a daring kind of...
I didn't think I was taking on enough risk just to be saying that no time is truth, so that was supposed to be a joke. So I took a big risk and wrote the epilogue, where I talk about what the idea of living in a universe where time is real and the future is at least partly open could mean for how we conceive of ourselves, for how we think of change in our own lives, for societal change, how we conceive of challenges that face us like climate change and like the instability of economic markets. And I'm proud of what I did there.
It's a very brave book, and I'm sure it will have a lot of impact on physics and beyond. And so thank you very much, Lee Smolin.
Thank you.